Okay, let's say it's fine where it is. The only thing is that I cannot see you on my screen right now. So yeah, if there is something, if you feel like there's something you need to interrupt, then please just open your mic and let me know. Okay?
Yeah, sure.
Yeah. Okay. Thanks for having me. I heard your backgrounds and everything, and they're all super related to the things that I'll talk about today. So I'm really looking forward to hear your thoughts about this work. A quick intro about me. I'm Stratis. I'm a postdoctoral researcher at the Hasso Plattner Institute. Here I am working with Professor Sandro Wachter. I'm in the technology and regulation group, and we're doing some interdisciplinary work, let's say at the intersection of computer science, law, and also philosophy. And we're very excited to be supported by the Alexander von Humboldt Foundation. But since I joined my new group very recently, today I will be talking about work that I did at the MPI for Software Systems. This is where I did my PhD. And I will be talking about two projects that have to do with LLM pricing today. And this is based on joint work with Ander, Nastaran, and Manuel from the MPI. And I want to give special credits to Ander. He has been the main, let's say, leading force behind these two projects. So yeah, special credit goes to him. Okay, so let me get started. As you may know, at the end of 2022, there has been a new thing introduced on the internet, which was ChatGPT. And this essentially led to an explosion of large language models, and they started entering multiple aspects of our life. But since that time, there have been multiple large language models by multiple companies that have been developed, and their performance is getting better and better every day. And large language models are essentially pieces of software, but they are different from other software that we may have had before in the sense that they cannot really run on conventional computers such as laptops or workstations, but they require stronger hardware because they perform a lot of computations. And specifically, large language models that we're working with today are working on GPUs. So an LLM requires a GPU to operate. And for the frontier models that present the best performance out there, one GPU is often not enough. So these models require a lot of GPUs in order to run. So the way that this works, because we cannot all have multiple GPUs in our homes or even in our companies, there have been specific providers, some providers who have built those big compute clusters with hundreds or even thousands of GPUs. And the way that we are using frontier large language models is that we essentially use them via our computers, but the actual software is running on a compute cluster that is based somewhere else. So it's running on the compute cluster of the LLM provider. This has created a market, a very new market, for what is called LLMs-as-a-service. So in this service, what is happening is that we have users who are posing queries. For example, the query here is, what does CISPA stand for? And providers run an LLM with that query on their own hardware, and they provide, after the LLM generates the response, they give it back to the user. I hope I got CISPA correctly. If this is wrong, please correct me at the very end, because I will be using this example throughout the talk. So let's say the question is, what does CISPA stand for? The provider says Center for IT Security, Privacy, and Accessibility. And this is the LLM as a service. And a natural question here is, okay, we have this service. How is it charged? How is it priced? So let's look at this example. Let's say that this person here is you. Your favorite LLM provider is Good AI. You're asking this question, what does CISPA stand for? And to understand how the process goes and how it is being charged, we need to understand first how this transaction essentially works. What is the process, the overall process? So when you pose your query to good AI, this is typically done via an API call. So here I want to clarify that I'm focusing on cases where the user is sending their queries via APIs, because, for example, they want to do this in bulk, in large numbers. And what I will be talking about next does not focus on simple scenarios where the user is using a chat interface like ChatGPT, where pricing is many times is free and it follows a different model. So I'll be talking about pricing in API calls. So you're sending this query to the provider, and the provider passes it to the LLM. The LLM starts doing computations in the sense that it starts generating tokens. So tokens are essentially pieces of text that an LLM is using in order to compose its response to the query that it received. So tokens can be words like center. Yeah, let's say here the second token is for, but they can also be subwords, for example, IT. And the LLM keeps generating one token at a time. And the important thing that I want you to keep here is that essentially the more tokens it generates, the more computations it performs. So the amount of computation done by the LLM is proportional to the number of tokens that it generates. So a natural way to charge such a service is essentially for the provider to say that I want to cover my expenses, the expenses I had for this computation that was performed. So you will pay me a fixed price per token. So let's say the model generated 8 tokens. I want to be paid 8 euros. The actual prices are much, much lower than that. But for the sake of this example, let's just say that 1 token is 1 euro to keep things simple. And this is known as the pay per token pricing mechanism. So here, essentially, there is a fixed price per token, and depending on how many tokens the model generates, we pay accordingly. Now, this was the transaction that happened. You asked your query to good AI, you got this response, and you got charged 8 euros. And the question that I want to ask here, and it is intentionally a bit provocative, is your LLM overcharging you in this scenario? And what I will talk about in the rest of the talk is what is the problem? So are there reasons to worry that an LLM might be overcharging us? And I also want to talk about solutions. So what can we do about this particular problem? So let me start with the first part. Here, to understand what is the problem, we need to understand a bit how LLMs generate outputs. So the important thing here is that responses are being generated stochastic. So we're giving a query to the LLM, and what the LLM does is that first it creates a probability distribution over all the tokens it has access to. So the LLM has essentially access to a vocabulary of tokens, which is thousands of tokens, and it creates a distribution like that over all its tokens in the vocabulary. So here the most likely one is center, then cyber, and there is C. So this vocabulary also contains subwords or individual letters or numbers or any other thing that you can imagine. So then what it does is that it simply samples from that distribution. So here, let's say that it samples center and it puts center in the response. Then it creates a new distribution for the next token. So let's say here it samples 4, then it creates a new distribution. Let's say it samples IT. It doesn't need to be the most likely one always. And then it samples security and so on and so forth until at some point the generation stops. So this is how the model generates its response token by token. So we asked this query to the provider. The provider ran the model that followed this stochastic process, and the model generated 8 tokens, and the provider told us this was 8 tokens I want to be paid 8 euros. The question here is, did the LLM actually generate 8 tokens? Can we be sure that what happened in the hardware of the provider was actually a generation of 8 tokens? How do we know that we are dealing with this good AI provider that is telling us the truth, and we are not dealing with some evil AI provider where essentially the model generated stochastically, again, 6 tokens, because this second tokenization that you see here is also possible. But then the provider decided to tell us that, what the model actually generated is not 6 tokens, but is 8 tokens. So they are essentially getting those 2 extra euros for free. Can we know in which of these 2 scenarios, which one of these 2 scenarios is the real? And the answer here is that essentially we don't know. So we don't really have a way when we see an individual output to understand if this was the actual tokenization generated by the model, because essentially any possible tokenization has some positive probability of being generated by the model. And the point here is that in this setting, we essentially have to trust that the provider tells us the truth. However, at the same time, this pricing mechanism that is based on the number of tokens creates a financial incentive for the provider to actually misreport the tokenization of the output and report a tokenization that is longer than the one that was actually generated by the model. And to illustrate this, I will introduce some notation here. So let's say that we have this query. We have the generated sequence that we will call, we will use the letter T, and this is 6 tokens. Then the provider applies to this a reporting policy that we will call pi, and the reporting policy generates a different tokenization that now consists of 8 tokens. And for this, we will use the letter T tilde. What the user pays in this scenario is essentially a payment that is linear on the length of the reported token sequence. So there is this constant here, R0, that is the price that the provider is charging per token. And the payment of the user to the provider is proportional to the length of the reported tokenization. And since we're talking about incentives, let's see what is the utility that the provider gains in this scenario. So the utility of the provider has a positive term that is simply the payment of the user to the provider. And it also has 2 negative terms. The first negative term is the generation cost. So the provider has to pay a cost for the true output to be generated. You can think of this, for example, as energy costs. And the provider also has to pay an additional cost, perhaps, potentially, optionally, that is a cost of running the reporting policy pi. So for now, let's say that this is 0. I will come back to this later and explain what it is. But assuming that this last cost is 0, what I want you to see here at the utility expression is that there is this generation cost that depends only on the true generated sequence, that the provider has already paid for that cost at the moment that the output sequence is generated. And then they have the freedom to report to the user some token sequence T tilde that essentially increases their utility the longer it is. So they pay the cost, and then they have the freedom to increase their utility arbitrarily. So what this means essentially is that a provider who wants to achieve the maximum possible utility has an incentive to report to the user something like that. So they can essentially say that each possible character in the output was generated by the model as a separate token. And this might look weird, but it's actually a tokenization to which the model assigns positive probability. However, if you work with LLMs, you'll probably be questioning what I'm talking about right now. So in other words, this kind of output may look suspicious to you. And the reason for that is that, yes, these kind of tokenizations are probable. There is some positive probability of generating them. However, this is very low. And the reason for that is that these tokens that are individual characters are extremely unlikely. So in order to get an output that consists of 50 of those tokens, one after another, this is essentially so unlikely that it never happens. So, and additionally, in certain cases, models generate output not by sampling from the entire distribution, but what they do is that they use specific sampling techniques, such as top P and top K, if you've heard of them before. I will talk about top P in the next slide. That essentially what they do is they filter out tokens that are very low probability tokens. So these outputs that consist of individual characters as individual tokens are not only suspicious or very unlikely, but if the model is using a sampling technique like that, these kind of outputs are essentially implausible. They cannot be generated by the model in the first place. So what I will focus on next is a sort of a middle ground, a more realistic scenario where the provider wants to misreport the tokenization of the output in order to increase their utility, but they want to make sure that what they report to the user is plausible under the given the generative process of the model. And the way that we instantiate plausibility here is by using top P sampling. So let me explain what top P sampling does very quickly. We had this distribution that assigns different values to different tokens. And let's say that we have a value of this parameter P that is set to 0.95. What top P does is that it essentially wants to find a small set of tokens whose cumulative probability is above 0.95. It's fairly simple. So what it does, it starts from the most likely token. The sum so far is 0.52. Then it goes to the next one. The sum is 0.96. We crossed the 0.95 threshold. Therefore, we are done. So it creates this set of those two tokens, center, the two expressions of center, essentially. And then it samples proportionally from only those two tokens, while it completely excludes all the tokens that follow after. Okay? That's the process of top P sampling. So we focus in generative processes that follow this kind of logic. And we also focus on scenarios where the user doesn't only receive the output in tokenization, but it also receives the next token probabilities that are generated, are given by the model at each step of the generative process. So here are those values, 0.52, 0.54, 0.25, all of them are also given to the user. What this means is that the user has a concrete way of questioning whether a specific tokenization that is reported to them by the provider was actually generated by the model, because they can check at each step of the generative process. They can check each vector of next token probabilities, whether the token that is present in the token sequence reported to them by the provider, whether it is in the respective top P set that follows from those probability. So it's a concrete way from the user to check whether the outputs reported to them by the provider are plausible or not. And for that reason, we are focusing on cases where the provider misreports to the user only output sequences T tilde that are plausible according to the probabilities of the model. The positive result here is that finding a tokenization that maximizes the provider's utility in this setting under this plausibility constraint is an NP-hard problem. And this is a first step showing that essentially there are computational barriers in the process of a provider to overcharge the user optimally. So the non-technical result here is that if we ask the provider to be transparent about the next token probabilities of the model, and there is also some special sampling technique like top-lead sampling going on, this makes it non-trivial for the provider to cheat, to lie to the user about the tokenization in a way that is optimal for their own utility. However, let's say we don't care about optimality. Let's say that the provider just wants to overcharge the user by a bit. They want to find a tokenization that is at least a bit longer than the one that is generated by the model, but is also plausible. So they want to do this in a way that doesn't raise suspicion and maintains the plausibility of the output. Is this possible? That's the question. And the answer here is that unfortunately it is possible. And to illustrate this, we developed a heuristic algorithm that does exactly that. And here I'll give you a brief description of the algorithm. So consider that the model generated this output that consists of 6 tokens. And what the algorithm does is that it starts by finding the token with the highest ID. So some background here, each token that the model has access to, so its entire vocabulary, comes with IDs. So I can go into more details later if you want during the Q&A, but here what we do is that we start with the token that has the highest ID. And let's say this is IT security. What the algorithm does is that it splits this token into 2 separate tokens that also have high IDs. And let's say that these are IT and security. What it does next is that it repeats this process m times. So in this example, I'll just keep m to 2 to keep things simple. So this will happen one more time. Now the token with the highest ID is accountability, and then the algorithm will split it into 2 tokens, which is account and ability. Let's say that this is done. Now what the algorithm does is it verifies whether this final sequence that it produced is plausible according to the model. So what it does is that it computes the next token probabilities at each one of these 7 output tokens to check whether the token that comes afterwards is in the top P set of that is given by the model if we pass it as input the respective partial output. So let's say that this is plausible, so that each token is fine, it's in the respective top P set. Then what the algorithm does is that it just reports this to the user. It's a plausible output, it's longer than the original one, we're good. If this output is, this modified sequence is not plausible, so there are tokens that do not belong to the respective top P set, then it reports the original sequence that was actually generated by the model, which we know by definition that is a plausible output sequence. So that's the algorithm. And the important thing here is that this final verification step requires GPU computations because we need to compute the next token probabilities that are given by the model. And this is the reason why we have this separate cost term in the utility of the provider that I mentioned earlier. So it might be profitable for the provider to do this process and report a longer tokenization. But if this cost of verification is too high, then their overall utility is low. So there is a trade-off here between running the algorithm and increasing the length of the tokenization. So let's see what this looks in practice. So we have some experiments. Here are with a model from the Gemma family. So what you see in these plots, on the x-axis is the number of iterations of the algorithm. So essentially the number of splits that the algorithm is trying to do in the tokens. And on the y-axis, you see the percentage of tokens that are being overcharged. So the percentage of tokens in terms of the percentage increase in terms of tokens that the algorithm is managing to find while making sure that whatever it reports is plausible, but given the probabilities of the model. And the different colors that you see here are different values for the parameter that determines the top P generation. So there are a few things to notice here. Essentially, the first thing to notice is that the revenue, the increase in revenue of the provider, reaches a peak. And the intuition here is that if the algorithm, so as the algorithm splits more and more tokens, essentially this gives additional revenue to the provider. But if the algorithm becomes too greedy, so if M is too large, then at this point, every output is implausible, essentially. And the algorithm resorts to reporting the outputs that were originally generated by the model, giving a 0% increase. So that's the idea why we are seeing a peak. And the other observation here is that as the generation becomes less restrictive, so as we increase the value of P, and we're allowing more tokens to enter the top P sets, this gives more flexibility to the provider to increase their revenue. And this is why we see a larger percentage of overcharged tokens for larger values of P. However, this here, what you see here is just about the revenue of the provider. So it's the increase in revenue, but it doesn't take into account this extra cost that I mentioned that has to do with running the misreporting policy, the algorithm that I described before. So what you see in this other plot is the actual percentage increase in utility of the provider, which includes this cost of running the policy, and of course, the cost of generation. Here on the x-axis, you see the provider's profit margin per token. What this is essentially the percentage of profit that the provider is making, essentially the fraction of profit per token over the price that the provider charges for each individual token. And what we see here is that essentially there can be a significant increase in utility of the provider whenever those margins are low. So whenever we are in a, let's say, competitive economy that drives the margins down, and the generation is less restricted. So there is room for the provider to find plausible tokenization. Seeing the pink line at the bottom, this means that essentially when the generation is very restrictive and the provider doesn't have much freedom, then for low margins, they cannot increase their utility. So essentially their utility is the same, and there is no incentive in overcharging users using at least this specific algorithm that we provide. So I hope that these results give you an idea of the problem and showcase to some extent why this paper token mechanism may be problematic, as it creates these hidden incentives for providers. And I want to focus in whatever time we have remaining on solutions. What can we do to actually solve this problem that I just described? So here I'll focus on two solutions. The first solution is kind of obvious, is okay, the pricing mechanism is broken, let's change the pricing mechanism. And the way that this would work is if we as users start pressing providers for a change in the pricing, in the way that the price these services. So the most reasonable requirement is that we should have some pricing mechanism that should make sure that the provider has nothing to gain by not being faithful, by essentially lying about the tokenization of the app. And if you, for any of you who has a bit of background in game theory or mechanism design, you are probably seeing that what we want here, what we're saying here, is that pricing should be incentive compatible. And incentive compatibility is a property that is very common, and it has received a lot of attention in mechanism design. What it means in our setup is that essentially whatever the generated sequence is, and whatever the policy of the provider, and whatever the modified sequence is, the utility of the provider should be lower than the utility they would have received if they were just following the faithful reporting policy. The faithful reporting policy is simply taking the output of the model and report it directly to the user, no lying involved. So the requirement here is, can we find a pricing mechanism that guarantees this, that essentially gives the provider maximum utility if they're telling the truth? And the result that we have here is that under some conditions about the pricing mechanism that perhaps we can discuss about later, there exists only one pricing mechanism that satisfies incentive compatibility. And this is a pay-per-character pricing mechanism. So instead of paying for a fixed price per token, users should pay a fixed price per character, let's say per letter or per number. Okay, so this is the first the first solution to the problem. But one could argue that this is a quite drastic solution. This requires the providers to completely change their pricing models. I don't think it's so drastic, but let's say someone could argue that. So what other solutions could we have that do not require a change in the pricing mechanism? And the other solution that we provide is that we can audit providers. So we can keep the pricing mechanism as is and create processes that audit providers to figure out whether they are misreporting or not. So consider that you have a provider that deploys a misreporting policy file, and this is characterized by what we call intensity. And this is very simple. It is essentially the average number of overcharged tokens per output. So it's the intensity essentially says how many tokens is the provider adding to the true tokenization. And let's say we have a provider who misreports using policy with such an intensity, and we have an auditor. What the auditor wants to do is that they don't know pi, of course, because they don't even know if the provider is faithful or not. But they want to know if the provider is actually overcharging users. And the way that we express this is essentially as a statistical test. So we have two hypotheses. The null hypothesis is that the provider is faithful. They're just reporting the outputs that are actually generated by the model. And this is the null hypothesis. And in this case, note that the intensity is essentially zero. So the faithful policy has zero intensity. And in the alternative hypothesis, we have a provider who is unfaithful. So in that case, the intensity of their policy is positive. And we want to distinguish in which of those two scenarios we are. The requirements here is that we want to do this in a sequential way so that we do not send too many queries to the model. And we want to do this with guarantees about the errors and the overall accuracy of the test. So how do we do this? I will describe here our auditing framework. So essentially, we consider that the auditor collects a dataset of queries and outputs from users. And here, by outputs, I mean tokenizations and their respective streams. And let's say that this collection happens by users who found that the tokenization they received is suspicious. And if many such users collect their tokenizations and report them, then let's say that the auditor decides to start an auditing process for this provider. What the auditor does next is that they go to the provider and they ask for white box access to their model. They want to run a test on the model to see if it complies with the requirement of being truthful to the users about the number of tokenizations, about the number of tokens that are included in each output. There are two parameters here that are important. There is this alpha parameter that controls the error rate of the test, of the audit. And there is this lambda I parameter that controls the speed of the test, how quickly it essentially decides if the provider is being faithful or unfaithful. And the way that this auditing process works is that the auditor starts by setting this variable m1 to the value 1 and starts running the test. What happens at each step of the process is that the auditor takes one of the queries and its respective output that is reported by the user, and it computes whether there is evidence that this tokenization is longer than it should have been. So they compute this EI value, which is essentially the length of the reported token sequence minus the length that this sequence should have on average, given the specific query and the string that is given as output by the model. So here, this second term, to estimate it, we develop an unbiased estimator that, given a query and an output string, it estimates what is the average tokenization length for this particular output. The next step, once we have computed this evidence, is that we aggregate it. So we had this M1 taking value 1, and now we multiply it by this term, which is 1 plus lambda I, multiplied by the evidence that we computed. And the way that the test stops is that we decide to stop it, essentially, if this process MI process a specific threshold alpha, that this threshold is larger than 1. And essentially, when we cross that threshold, we flag the provider as being unfaithful. And that's the overall process. Now, detail here, if we never cross that threshold, essentially we can set a maximum number of steps that after that point, if we haven't crossed it, we stop. So let's see what this means when we are auditing a faithful and an unfaithful provider. We start from the case of the faithful provider. There is this good AI company, and we want to run this audit. Essentially, what happens is that for each one of the queries, we compute whether there is evidence that the tokenization is longer than it should. Since the provider is faithful, this intuitively means that the evidence should be around 0. So the reported tokenization should be, on average, the same as the length that it should have if we just sample the model. Okay, so the evidence should be around 0. In the aggregation step, this means that essentially this MI will stay close to 1 because the evidence is close to 0. And since this alpha value that we have for the threshold is higher than 1, this means that we will, it's very unlikely that we will actually ever cross that threshold. So if we're auditing a faithful provider, we will keep running queries to this provider, and we expect that we will never cross the threshold. So our test will never conclude that this provider is unfaithful. The theoretical result here is that if we set these lambda I values small enough so that these terms of 1 plus lambda multiplied by epsilon are always positive, then we can guarantee that the probability of actually crossing the threshold is very low, is bounded by 1 over alpha. So essentially, this threshold alpha that we set controls the false positive rate of the audit. This is the theoretical characterization of the audit. And what this means in practice is the following. Here, I have an experiment with a Mistral model, a model from Mistral. And what you see is on the x-axis, the number of time steps, which corresponds to the number of queries that we are running during the audit. And on the y-axis, you see this test process M, which is the MI that we talked about before. So essentially what this plot shows is that across multiple realizations, this test process always stays close to 1, and it never crosses the threshold, or it doesn't even come close to crossing the threshold. As you can see, in only one realization, this MI goes close to around 8 or 9 or 10, while the threshold here is 20. So it essentially never concludes that the provider is being unfaithful. That's good. That's what we want from a test that audits a faithful provider. Now let's see the case where the provider is actually unfaithful. So we have this evil AI that adopts some misreporting policy with positive intensity and increases the length of tokenizations generated by the model. So it reports something longer to the user. What happens in the process of the test is that, again, we compute the evidence. Since the provider is reporting tokenizations that are longer than the ones that the model actually generates, this essentially means that this evidence variable will be above zero because the length is is higher than what is actually generated by the model. And during the aggregation step, this means that essentially this MI will start accumulating that evidence. So we'll have these positive values. We will keep multiplying by something that is larger than 1. So we expect this MI to start going up. And over time, we expect that MI will eventually reach the threshold alpha that we have set as a stopping criterion for our audit. Okay? And the theoretical result here is that if we set this lambda I values to a constant that is sufficiently small, essentially this guarantees that this audit process always detects misreporting, and the number of queries that is required to cross the threshold alpha is upper bounded by a quantity that here it's very simplified, but the point that I want you to notice is that it depends on the intensity of the misreporting policy of the provider. So essentially, if we have a provider who misreports with high intensity, this means that we need much fewer queries to detect that they are actually misreporting. And here, a bit of additional intuition. You see that there is this log factor, that it depends on the log of the intensity. And the idea is that essentially the evidence variable is, let's say, on average proportional to the intensity. So if you start accumulating, this ends up, the process M ends up growing exponentially to the value of the intensity of the policy. So to make this perhaps a bit clear, let's see an experiment with a simulated unfaithful provider. So here it's an experiment with a llama model. What you see on the top plot is the test process, so the values of this MI over time. And with the 3 different colors, you see 3 different providers who are misreporting with intensities that are positive. So these providers here are using the misreporting policy that is based on the heuristic algorithm that I introduced in the first part. And what you see here is that essentially in all cases, the process MI reaches the threshold 20 that we have set for the audit. So in all cases, the audit eventually detects that the provider is being unfaithful. And on the bottom, on the plot at the bottom, you see the time that it takes until the process reaches the threshold alpha. And what is worth noting here is that essentially as the intensity of the process, as the intensity of the misreporting policy becomes lower, it is harder for the test to detect that the provider is misreporting. But the other interesting thing here to see is that essentially when we have a provider who is misreporting with a very low intensity, 0.8, so essentially they are adding less than 1 token to each output, it takes us at most 70 queries to detect it. So it's an audit process that is very fast, even if the provider is being very subtle in the kind of misreporting they do. We only need a few number of queries to detect that they are actually lying. So these are the observations from this experiment, and I will leave it here with some quick takeaways. So the first thing that I want to mention is that GenAI has created some new markets, and I want to emphasize that these markets, like the one for the LLMs as a service, are very new. They are not like the markets that we are used to for ordinary products, but these are markets that were developed in relative terms essentially yesterday. So they are not perfect. There are aspects in those markets that we should be thinking about, such as pricing. And these aspects also bring several hidden incentives. And it's a very interesting area to try to analyze what is problematic about those markets and what we can do to actually improve them. And the other takeaway here is that it's a bit more technical. I think sequential hypothesis testing is a super interesting area. And this was actually our first project in which we entered this area and tried to use it for some interesting application. And I think it's a very interesting tool, a useful tool for developing auditing processes that come with guarantees, with statistical guarantees. That's it. So here are the two QR codes for the two papers that I talked about today. And I'm happy to stop here and take any questions you have. Thanks.